Hello friends, in the last lecture we have studied about Gauss theorem. Gauss theorem simply helps us to find out the net charge enclosed in a closed surface with the help of the electric flux, or you can say by the help of the amount of electric field lines coming out of the enclosed surface. In this lecture, we are going to study various important applications of Gauss theorem. The first we are going to study is the electric field due to an infinitely long uniformly charged wire. But before starting it, let us first understand what is a uniformly long straight charged wire. A wire can't be of infinite length. प्रैक्टिकली पॉसिबल नहीं है कि कोई ऐसा वायर ले जिसका लेंथ इनफाइनाइट हो. इट इज़ नॉट प्रैक्टिकली पॉसिबल. Then what basically an infinitely long wire means? As you can see, I have drawn this diagram. I have drawn a straight line over here. Let us assume that this is a wire. Now if I keep a point very close to it, and if I want to see the ends of the wire, then this line will be the line of sight. And as you can see clearly over here, this angle is almost 90 degree. It means if I keep a point very close to a wire which is of finite length, the wire will appear to be of infinite length for the point. As you can see over here, for this point which is very close to this wire, the ends, if we see the ends, the angle is almost equal to 90 degree. So such type of wire which is practically of finite length but can be considered of a infinite length. A wire is considered to be infinite length if L is much greater than R. L here is the length of this wire. The length of this wire is considered to be L, whereas the distance of this point from the wire is considered to be R. So if the length of the wire is much greater than the distance of the point from the wire, then a wire can be considered to be of infinite length. Though practically it is not of infinite length, but it can be considered. I have written over here, as you can see, the position of point P. Let's say this point is P. If the position of point P is very close to the wire and the angle of sight, this angle of sight from point P of the ends of the wire is almost 90 degree, then such a wire can be considered to be of infinite length. Though the wire is of finite length, since the point P is very close to this wire, so for this point P, this wire will behave as a wire of infinite length. So this is a basic concept how to understand an infinitely long straight wire. Though it is not, it can be considered as a wire of infinite length. So moving on, let us say I have taken a wire which is uniformly charged. It has positive charge all over it, uniformly distributed, and I've taken a point, this point P, which is supposed to be at a distance of R from the wire. Now if this distance is very small as compared to length of the wire, this wire will behave as an infinite wire or a wire of infinite length. Okay, so this wire is considered to be of infinite length. Now I've taken 2 points, any 2 points A and B, which are at equidistance from any point O. This point is not compulsorily the center point of the wire. It can be any point. कोई भी एक point consider किया है जहाँ से इस point P का distance R है. उस point के ऊपर और नीचे we have taken 2 points which are at equidistance. Let us assume that these 2 points A and B are at a distance of x from this point O. Let us find out intensity of electric field at point P due to A and B. As we know, since it is a positively charged, the electric field direction will be radially outward. So due to point B, it is in this direction. Due to point A, it is in this direction. On resolving them into the components, as we can see, EB cos theta and EA cos theta, which are vertically opposite to each other, will cancel out and the sine component will add up. From this, we have come to a conclusion that at any point P, which is at a small distance from any wire which is uniformly charged, the direction of electric field intensity will be vertically outward. This will be the direction of the net electric field due to this wire which is positively charged at any point P. If it was negatively charged, the direction would have been towards inside this direction. Since we are considering the wire to be positively charged, so at any point P, which is at a small distance r from the wire, the direction of electric field will be vertically outward. If we talk about direction, we have considered 2 points A and B which are at equidistance from point O. The direction of electric field due to A and B at point P is shown. We have discussed. The horizontal component will cancel out each other, whereas the vertical component will add up. So this will be the main direction of electric field intensity due to this charged wire. So we can say the direction of electric field at any point due to an infinitely long wire will be radially outward. We have come to this conclusion that the electric field intensity at point P will be vertically outward. But what will be its numerical value, or what would be the formula for finding out the value of electric field? For this, we will use Gauss theorem. Gauss theorem is applicable only on Gaussian surface. Means we have to find a closed surface around any point at which we need to find out the intensity of electric field. So coming to this diagram, we need to find out electric field intensity at point P, which is at a distance of small r from an infinitely long uniformly charged wire. I have considered a small area element ds around P. Now we need to draw a closed surface, a Gaussian surface. So by symmetry, the Gaussian surface for this point around this wire will be a cylinder. Let me show you with the help of an example. Let us consider this is a uniformly charged wire. Now I need to find out electric field intensity at my fingertip. So symmetrically, I will need to draw around this. So symmetrically, this will be the direction and this part will behave as a closed surface, and the shape of this closed surface will be a cylinder. So here this is the red cylinder shown as the Gaussian surface. It is not compulsory that the Gaussian surface should cover the entire wire. It can only cover a small portion of the wire. So let us assume that this Gaussian surface have enclosed L length of the wire. Now how to find out electric field intensity at point P? So we know that the net flux to the Gaussian surface phi is equal to phi A1 plus phi A2 plus phi A3. Now what are A1, A2 and A3? As you can see in this diagram, there are three closed surfaces. The upper part, circular part is considered as A1. The lower circular part is considered as A2. And this curved part is considered to be A3. The total flux will be the flux coming out of A1, A2 and A3. So total flux phi is equal to phi A1 plus phi A2 plus phi A3. टोटल फ्लक्स कैसे निकालते हैं? हर एरिया से फ्लक्स को निकाल के ऐड कर देंगे. तो फ्लक्स ड्यू टू A1, फ्लक्स थ्रू A2 एंड फ्लक्स थ्रू A3. देयर आर 3 क्लोज सरफेस ओवर हियर, 2 सर्कुलर एंड 1 cylindrical portion. Now phi A1 and phi A2 will be equal to 0. Now why is this so? As we have already discussed, the direction of electric field will be radially outward in this direction. So if I talk about area A1, then what is the angle between electric field lines and area? As you can see, it is 90 degree. And as we know, phi is equal to EA cos theta. Here theta is equal to 90 degree. So the flux coming out of this area A1 will be equal to 0. Similarly for area A2, this is the direction of electric field lines and this is the direction of area vector. Again the angle between them is 90 degree. So again the electric flux coming out of this area A2 will be 0. So phi A1 is equal to 0. Similarly phi A1 is 0 and similarly phi A2 is also 0, as the angle between area vector and electric field intensity is 90 degree. So we can say now that phi is equal to phi A3. So phi is equal to phi A3 and the formula for finding flux is E dot ds. So written E dot ds. Now ds is the small area element around this. As you can see, this n3 gives the direction of area vector of A3 and this is A. So the angle between them is 0. So E dot ds will be E integration of ds. E is constant, so I have taken out. The integration of ds will be the curved surface area of the cylinder, which is equal to 2 pi r h. Here h is equal to L. As already is mentioned in the diagram, h is equal to L. So E is equal to 2 pi r L. 2 pi r h, but I have written L as the length of the cylinder is taken to be L. So it will become E is E into 2 pi r L. So the net flux coming out of the Gaussian surface is equal to E into 2 pi r L. Now by Gauss theorem we also know that phi is equal to Q by epsilon naught. Since the wire is uniformly charged, so how to find out charge? We have studied in earlier lecture about continuous charge distribution. In this case, since it is a linear charge distribution, we'll use the formula for linear charge distribution, which is denoted by lambda, and it is equal to Q by L. Total charge upon total length. So Q upon L. Therefore Q will be equal to lambda L. Putting this value over here, we get phi is equal to lambda L upon epsilon naught. Now equating equation 1 and equation 2, we'll get E into 2 pi RL is equal to lambda L by epsilon naught. On solving, we'll finally get E is equal to lambda upon 2 pi epsilon naught into R. So using this formula, we can find out intensity of electric field at any point due to an infinitely long uniformly charged wire. I'll again repeat, it is not actually a infinite wire, but since the point is very close to the wire, it is considered to be of infinite length. And the formula for it is E is equal to lambda, where lambda is the linear charge density of the wire upon 2 pi epsilon naught into R. R is the distance of the point from the wire at which we have found out the intensity of electric field. Next we are going to study how to find out electric field intensity due to a uniformly charged spherical shell. What basically a spherical shell is? It is just a hollow sphere. Now the point at which we need to find out the intensity of electric field can be anywhere. It can be outside the shell, it can be on the surface of the shell, or it can be inside the shell. So we will discuss each of them separately. First we will find out the electric field intensity at any point outside the shell. As you can see in the diagram, there is a spherical shell of radius capital R. it is charged, or it is given a charge q. As we know, in the case of conductor, whenever some charge is given to it, the charge gets readily distributed over its surface. So if q charge is given to the shell, it will be uniformly distributed on its surface. So as you can say, positive q was given to it, it got uniformly distributed on the surface of the shell. Now I need to find out intensity of electric field at any point P, which is outside the cell and is at a distance of r from the center of the shell. For using Gauss theorem, we need to find a Gaussian surface. So this dotted sphere or shell is now behaving as a Gaussian surface in which this point P lies. I've taken a small area element ds around point P. Since the shell is positively charged, the direction of electric field will be radially outward, which we have discussed earlier, and this n cap shows the direction of area vector ds. So moving on, we have considered a point P which is at a distance r from the center of a uniformly charged spherical shell of radius capital R. Imagine a sphere of radius small r around P, which is the Gaussian surface. This dotted sphere or the shell is the Gaussian surface on which the point P lies. Consider a small area element ds. I have already discussed around P. The direction of electric field and area vector are shown in the diagram. This is the direction of electric field and n is the direction of area vector. Now according to Gauss theorem, electric flux is equal to E dot ds is equal to q by epsilon naught. So E dot ds is the small element around P. If I surface integrate it, it will be equal to the surface area of the Gaussian surface. So surface area of the Gaussian surface, since it is a sphere, the surface area is given by 4 pi r square, where in this case the radius of the Gaussian surface is small r. So ds is equal to 4 pi small r square. Putting this, I will get E dot 4 pi r square is equal to q by epsilon naught. On solving, I finally get E is equal to q by 4 pi epsilon naught r square. So this is the formula for finding out electric field intensity at any point which is outside the uniformly charged spherical shell. We have come to a very important conclusion from this derivation, and the conclusion is this: though the charge was uniformly distributed on the shell, but the formula indicates that the charge was concentrated at the center of the shell, though it was not. The formula indicates that for point P, the distributed charge appeared to be concentrated at the center of the shell. Moving on, we will now find out the electric field intensity on the surface of the shell. If the point is on the surface of the shell, then the radius of the shell will behave as the distance of the point P from the center of the shell. So small r will be equal to capital R. On solving that or putting the value of small r in the previous equation, we'll get E is equal to q by 4 pi epsilon naught r square. Using this, you can find out the intensity of electric field at any point which lies on the surface of the uniformly charged shell. As we know that the charge was uniformly distributed over the entire surface. If the charge was uniformly distributed over the entire surface, the surface charge density will come into play. And as we know, surface charge density is given by Q is equal to charge upon area. The area of the shell is surface area is 4 pi r square. So Q becomes 4 pi r square into sigma, where sigma is the surface charge density. Putting the value, we'll get sigma upon epsilon naught. So we can use this formula also for finding out electric field intensity at any point on the surface of the shell. What if the point is inside the shell then? This is a diagram for it. The point P is now inside the shell and the distance of the point P from O is R. Since the shell is a conductor and the charge is uniformly distributed on its surface, there will be no charge inside the shell. And we can also say that there will be no charge inside this Gaussian surface, this dotted form, which I have drawn a small sphere or shell inside the main shell. There is no charge enclosed. And if there is no charge enclosed, then as per the Gaussian theorem, phi will be equal to 0 and hence electric field intensity will be also equal to 0. So at any point inside the shell, there is no intensity of electric field, or you can say the intensity of electric field will be 0 inside the shell. On the surface of the shell, it will be equal to Q upon 4 pi epsilon naught capital R square, where capital R square or capital R is the radius of the shell. Inside the shell, the electric field intensity will be 0. Now let us find out electric field intensity due to a thin infinite plane sheet of charge. What is this infinite plane sheet? As we have discussed, let's say this is a sheet of some finite dimensions. If I consider a point P which is very close to this sheet, then this sheet will behave as a sheet of infinite dimensions or infinite area. This we have already discussed in detail for a uniformly charged infinite wire. If this point P is very close to this sheet will behave as a sheet of infinite dimensions. Now I need to find out electric field intensity at point P. For this, I need to draw a Gaussian surface of symmetry. As you can see, I have drawn a cylinder of length 2r around this point P. Now there are two faces of this sheet, front face and the back face. Both of them are uniformly charged with positive charge uniformly distributed. So at this point P, which is at a distance of r, the electric field intensity will be vertically outward, and this n cap shows the direction of this small area ds around P. For this surface, due to this charge, the electric field intensity will be vertically outward, but in this direction. It is quite obvious. And this n cap indicates the area vector. Now the cylinder can be divided into three parts, two spherical part and one curved part. I have given them name 1, 2 and 3. So the point P is at a distance of r from the sheet. Let us imagine a cylinder of cross sectional area A. The area of this cross section of the spherical part is A and the length 2r around P. This will behave as your Gaussian surface. Now the net electric flux will be equal to the flux through this area 1, area 2 and area 3. So phi will be equal to phi 1 plus phi 2 plus phi 3. Phi 3 will be equal to 0. As for this curved surface, area vector will be along this direction, and in a angle between intensity of electric field and area vector is 90 degree. So the net flux passing will be 0. So the net flux passing to third area is equal to 0, and 1 and 2 are similar to each other, so I have add up. So finally I'll get phi is equal to 2 integration of E dot ds. Since E is constant, I have taken it out. So phi is equal to 2E dot ds. As we have already written, the cross sectional area of the cylinder is equal to A. So instead of ds, we can write A. So phi is equal to 2E dot A. Now using Gauss theorem, phi is equal to Q by epsilon naught. Since the charge is uniformly distributed, so we'll use surface charge density, which we have done in earlier parts also. So surface charge density sigma is equal to total charge upon area. So sigma is equal to Q upon A. From here we'll find Q is equal to sigma A. So instead of Q, I'll write sigma A. Now if I equate equation 1 and 2, I'll get 2EA is equal to Q by epsilon naught, and instead of Q, we'll write sigma A. So 2EA is equal to sigma A by epsilon naught. On solving, we get E is equal to sigma by 2 epsilon naught. This is the formula for finding out electric field intensity due to a thin infinite plane sheet of charge. And this sheet will behave as infinite only when the point P is very close to the sheet. Now what if the plane sheet is of uniform thickness? It is not thin. Then how we'll find out electric field intensity? I have drawn this sheet which has a certain thickness. So how to solve this? In this case, we'll use the front face as well as back face, and we will consider them as two thin sheets of infinite length. This first face will behave as one sheet and the back face will behave as the second sheet. So the net electric field intensity at point P will be electric field intensity due to the first phase plus the electric field intensity due to the second phase. Since both of them are positively charged, the net electric field will be vertically outward for both of them. Hence, the net electric field will be E1 plus E2. As you know, E is given by sigma by 2 epsilon naught. So finding out, we'll get sigma by epsilon naught. So if the plane sheet is of uniform thickness, we'll consider the front face as one sheet and the back face as second sheet, and we'll find out the net electric field intensity by vector addition. Let me give you one more example. Let's say there is these are two sheets which are at some distance. Both of them are positively charged and are kept at some distance d apart. Let's say this is sheet 1 and this is your sheet 2. Now I need to find out electric field intensity at this point. Now how would I find out? See, the net electric field at this point P due to first sheet will be in this direction, and due to this it will be in radially outward direction. So net E will be equal to E1 minus E2. What about if the point is over here? Then due to 1 it will be radially outward, due to 2 it will be again radially outward. So here E will be equal to E1 plus E2. What if the point is over here? Due to 1 radially outward, due to 2 radially outward. So here E will be equal to again E1 plus E2. This will happen only when there are two infinite thin sheets which are at some distance, and we need to find out electric field intensity at any point which is either at the center of the two sheets or on the two sides of the sheet. At the center of the sheet, E1 minus E2, as due to sheet 1 it will be radially outward in this direction, due to sheet 2 it will be radially outward in this direction. So these are some of the applications of Gauss theorem. Thank you students for listening patiently. Thank you.